Good morning, everyone. So my name is Minamoto. So I'm from National Institute of Materials Science in Japan. So, but it's 4 o'clock in Japan, so almost evening. So today I would like to talk about our ongoing national project related to the structural materials. So I would like to talk about the development of a system for performance analysis of structural materials, and of course developing APIs. So we are having a concept of materials integration. This is not familiar with you, I think, but materials integration, but the concept of materials integration is very similar to the ICME or something like that. So it means for structural materials, for understanding structural materials, we have to understand about the PSPP. And the PSPP is the process and the structure and property and performance. And here, maybe you will imagine about the structure. So for example, the electronic structure or crystal structure or something like that. However, for the structural materials, we define the structure is the microstructure. It means the very mesoscale problems. And the process is the pre-information in order to understand the structure. So it means the process means for example, the array composition or heat treatment history or something like that. And property is for example, for fatigue life limit or stress strain curve or hardness or something like that. And performance is the final materials performance, including the environmental or geometrical condition or something like that. In order to do that, so we will use 4 scientific paradigm. For example, this is the experimental and theoretical and the numerical calculation and data sciences. So this is just a very, very old figure to illustrate the process, structure, property, and performance relations. So I have mentioned that the process is the information about the array composition or heat treatment or something like that. And the structure means the information about the microstructure, what kind of phases are included, how the segregation is, or the distribution of the grain size or the precipitation or something like that. And after that, the properties are determined by the structure. So including environmental or geometrical boundary conditions, final performance will be derived from properties. So based on this diagram, so people sometimes define the different definition about the process or structure or properties. However, so we defined about the process or structure and properties. So we define the process is that maybe the people can determine as he wants or she wants. For example, the array composition is determined by the researchers or experimenters. However, the structure is the information about uniquely based on the some dynamical calculation or kinetics calculation or something like that. And property is derived from the structure information as a result of some kind of operator is worked for the structure information. So that is the properties. So based on this kind of concept, we have started to build our web-based computer system to analyze the structural material performance. So we have 4 teams. One team is the people are gathering to make the program to predict the microstructure. It's a mesoscale calculation. For example, the Kappa calculation or phase field calculation. And the second is the people were gathering in order to analyze the performance of the materials, including the geometric condition or environmental condition. We use the FEM calculation in the team. And the third team is the very supportive team, because the data for the structural materials is very sparse. So in order to apply for example, the machine learning techniques, so sometimes the number of data is very few. So in that case, we have to use other technique, for example, the data assimilation or sparse modeling, something like that. So to support these two teams, we have third teams based on theoretical information, theoretical analysis. And the biggest one is the team to integrate these three information in one web-based computer system. And as examples, so we tried to tackle four problems for structural materials. One is fatigue life prediction, and the second is creep life prediction, and third is hydrogen emprisonment problems, and the final is the brittle fracture for the weld joint part. So because the steel weld joint part is the most difficult problem compared to, for example, the aluminum alloys or magnesium alloys or some other nickel alloys. So we think that if we can understand the weld joint problems, we can maybe tackle to another problem. And so this is 1, 2, 3, 4 teams, and we, of course, we have databases corrected from the experimental. So we made a system to connect many modules, theoretical modules or experimental data, or some other, for example, commercial software or in-house software as a workflow. So the workflow is very important. So the main system, the web-based system, manage the workflow design or workflow plate or results of the calculation. So why we need the workflows? So workflows for multi-scale and the multi-physics calculation lead to, of course, the automation. And so if the automation is realized, so of course we can make we can make lots of calculations. So it goes to the optimization of parameters for the process or structures or something like that. And it is very useful to accumulate data for you in order to make the prediction models from machine learning technique. And this these three terms is very normal, and the second one is very important. Of course, we think it's important because many well experienced guys are retiring in these days. So we have to store or we have to accumulate the knowledge of the well experienced experts. So we are aiming to reproducing their knowledge in silico by linking computer programs and data and machine learning models. So in order to do that, the clarify restricted condition fracture problem is very important, because of course we can use many kinds of fundamental technique, just like for example, of course, first principle calculation, or the Kappa technique or phase field, FEM, or some other empirical formula. However, sometimes it restricts conditions very much. For example, the zero Kelvin ground state, or some restriction is, for example, the binary system. So in order to link the computer programs, we have to understand what kind of restricted conditions that each module, each fundamental programs has. So Now, of course, in order to calculate the from scratch to the end, so of course we have to such kind of restriction is not preferable. So we have to consider the missing physical models by linking these kind of programs. And here is the just one example of our system. So we the system is component mainly the three parts, and three part means the designer, in order to design the workflow and they play workloads. This is one component, and of course we have a viewer, and I'm sorry, this is one component, and so in order to understand the restrictions of the physical model or data, or I mean the metadata, so we store the vocabulary. We are calling the vocabulary inventory system. So each modules or each data, this yellow part shows the module, I mean the calculation program, and the blue one is the input condition, and the gray one is the output. So of course, these kind of tools have the theoretical background, and the data, input data has metadata, what kind of steers, what kind of heat treatment they have, or something like that. So we store this kind of metadata or physical background or something like that in the vocabulary inventory data. So this is very important, and of course we have to store the calculated data. So the three part is the player, designer, and player, and viewer. And here's one. And vocabulary inventory system and the calculation data. And here's the just a schematic illustration how the system is controlled. The modules, I mean the calculation program, each calculation programs and workflows. So in order to, this is just an example to calculate the crack propagation at the weld joint part. This workflow shows for example, the geometrical condition and the thermal condition. And here is the crystal plasticity calculation. And here we can calculate the crack initiation depending on the crystal structure, the phase situation. And finally, crack propagation is derived without the information about the phase situation, and only the stress information. So we connect to these kind of two fundamental programs in order to calculate as a multi-scale calculation, and how each module are described here. And so in here, so the researchers consider the process to calculate the crack propagation program. I mean the stress number curve, fatigue life limit, to build the connection of each modules and the passing how the data is passing. So the system can carry out these kind of modules automatically and gets the output data. Okay, and here's just an example, different example of the workflow in order to capture the fatigue life limit prediction, courtesy by Shibanuma. Professor Shibanuma, University of Tokyo, and the blue one is the input condition, and the yellow one is the calculation program, and the gray one is the output. And okay, so this is the picture of our system. So as I mentioned, if this kind of workflow is built at once, so we can calculate iterate. So we made, for example, we made for almost 550 cases calculation to make prediction model by machine learning. So this is just an example of the machine learning results. And we use the R to in order to make the prediction model. So user can understand the results of the machine learning. I mean the accuracy of the machine learning. If user can say it's okay, the accuracy is enough for my calculation, so user can switch to the machine learning model instead of the actual FVM calculation. It takes several hours to finish the calculation. So users can shorten the calculation time. Okay, so we made the workflow management system in order to shorten the calculation time or parameters optimization. And the workflow management system, all the elemental technologies are connected with the vocabulary information based on the PSPP linkage. Okay, and generated machine learning models are used as prediction models in the system. So it leads to the reducing calculation times. So this is our system mainly in order to solve the multi-scale problem as a forward problem, okay, by designing the workflow. So the main system consists of workflow designer player and vocabulary inventory system and database for experimental and calculation results. And as a subsystem, we made several specific software. For example, the machine learning regression program for our system, or specifying the program of the fatigue life well-joined fatigue life analysis, something like that. And we built the APIs in order to help the big calculation for the users. And our second stage, our national project as a second stage has just started. So we are aiming at this second phase to build APIs to control our system. In the red line, so this is the materials integration system that I have mentioned. However, if a user wants to solve the impulse problem, so user have to make a very, very large scale calculation, lots of calculations, and sometimes the scenario is very, very complex. So it is difficult to reproduce this kind of scenario or very big data, big calculation. So we made APIs, so user can use APIs, and user can make a very, very big calculation by making a program by himself. And so the APIs to handle our system is almost three parts. The first one is workflow APIs. The APIs to control the workflow execution. Here is just an example how to execute in Python script. And second one is database API. So we are aiming to access databases having different format or schemas. A very difficult problem, as you know. So we are now at a very, very early stage, I think. So however, we would like to access to the several databases having different formats. And finally, the inventory, vocabulary inventory API that I don't talk much more about this API because of the time limitation. However, we can make the graph data gathering the vocabulary information and analyze the background of the workflow data or something like that. And here's just an example by utilizing the worker APIs, it's very simple to optimize the, for example, analytic function, just like a Rosenberg function, to search the minimum of the function. It goes well, I think. And here is just an example to apply the actual materials program in order to search the preferable condition of the heat treatment of the weld joint part. And here is the APIs of the database. So why the API is better or better instead of the query building or something like that? So because the API helps to multiple databases. And if user already has several programs with use of the API, if the database structure is changed, and the database API can handle such kind of changes, so user don't need to change his program. So it's better for users. So this is why we are constructing database APIs. And at this moment, so we are thinking to change the database concept. Okay, so at the first stage, so we accumulated data, mainly the experimental data, which was performed in NIMS in Japan, and we built relatively big data, experimental databases in RDB format. But sometimes the structured database contains only PP information. And it means the process information and performance information or property information. For example, the composition of alloy or operating temperature and the applied stress is written in the database, and the performance record are written in the database. So, yeah, of course, we can understand by making the machine learning technique, understand the relation between process and performance by making machine learning techniques. However, at that times, we cannot understand the physical background or mechanism of the phenomena. So we are thinking to generate, to structure information, for example, the sum dynamics calculation or atomistic information. And by deriving such kind of data, structured data, may be connected to the performance information by machine learning techniques. So at that time, we can understand the backgrounds of the physical phenomena. So it's required for the researchers of the structural materials, I think. And also, we are thinking to increase the number of databases to be searched. In order to do that, so we have to make the database APIs. And here's just an example of the conversion of the property data to structured data. And this is just a first stage, so not enough information, however, we have just started. So once we got the property data from materials DB, for example, the NIMS MATLAB data, we can get the composition data or heat treatment data or stress data. So after that, so of course we can calculate for example, equilibrium states, what kind of phases are existing, how much the phases are. So if you understand such kind of information, for example, here's M23C6 carbide, so we can understand the moles or driving force by the calculation from the carbide calculation. And of course, we can get the information about formation enthalpy or some other information related to the, for example, the bulk modulus or shear modulus or strength of the materials. And of course, this is just a trial that our in our project. However, so instead of the equilibrium state, we need, of course, the topological information. So now we are, this is second stage. The first stage is the very, very early database, the process property linkage. So experimental database is related to the performance data by the machine learning. However, now we are changing this kind of process data into the structured data in order to understand the background of physical meanings. Okay, and in the future, so we are thinking to add the space features information based on, for example, the image analysis or phase field simulation or a diffusion control, the transformation calculation or something like that. Because the structural materials is very, we have to, I'm sorry, so we have to think about inhomogeneous or heterogeneous structures in order to understand the performance of the structural material. So we need the data or data format, the data schema, to express such kind of the inhomogeneous. So yeah, this is just the first trial to get such kind of information by using the phase field models or statistical calculation. So after that, this kind of structure information is analyzed by the machine learning technique in order to understand the performance. And here is just an example to predict the molten site start temperature in steels. And the left one is the descriptor of the prediction model is the composition. And the right one is the descriptor of the prediction model is thermodynamics quantity. The number of descriptors is less than composition here. However, so we can regenerate this is the experimental and here is predicted. So if you can see the data on this line, so the prediction model is perfect. So the accuracy of the two models are very similar instead of the fewer descriptors. And thermodynamic quantity is, for example, the existing moles of phases or driving force of the, for example, the carbides or some other intermediate compound. And I'm sorry, the red one is the trained data and blue one is test data. And here's just one example. So we have to think about, for example, the diffusion data or some other non-equilibrium state or something like that. Yes, and here is the that I mentioned. So we have to expand the prediction model by inserting the physical model in order to understand the background. So in order to do that, we convert the process information to structure information to understand the property or performance of structural materials. Okay, and here's another features of our system. So I said that we are gathering the vocabulary related to the physical models or input files, input data. So if the vocabulary, exactly the persistent ID, match to another input files or metadata, so the system can connect automatically the different modules or different the programs. Thank you very much. So this is summary. So our system GUI supports the direct programs, and APIs helps to develop the very complex scenario for inverse programs. And the data management will be carried out by searching multiple database, and the structured data generalization is very important in order to understand the performance of the structural materials. Thank you.